This video is about covalent bonding. By the end of this video, you should understand how a covalent bond differs from an ionic bond. You should understand how electronegativity difference determines bond polarity, and you should be able to identify partial charges on covalent bonds. In a covalent bond, electrons are shared between two atoms. This is as opposed to an ionic bond, where electrons are transferred from one atom to another. Here we see hydrogen is sharing its one valence electron with oxygen to form a bond. Again, another hydrogen on this side shares its valence electron with another of oxygen's valence electrons to form a second bond. Note that each bond consists of a shared pair of electrons. These electrons can be shared evenly or unevenly. This determines whether or not the bond is polar. Bond polarity is a measure of how equally or unequally the electrons in a covalent bond are shared. The polarity of a bond is determined by the difference in electronegativity. Recall that electronegativity describes the ability for an atom in a bond to pull electrons towards itself. When two atoms have the same electronegativity, they will equally attract electrons, making our bond nonpolar. When atoms have very different electronegativities, they will attract the electrons unequally, making the bond polar. Larger differences result in more polar bonds. Generally speaking, we say that bonds with an electronegativity difference greater than 0.4 are considered polar, though of course since this is a continuum, it's hard to draw a cutoff on a continuum. It is important to note that the CH bond, which is a very common bond, has an electronegativity difference of 0.4, and is generally considered nonpolar. Likewise, anything with an electronegativity difference greater than 2.0 is generally considered an ionic bond. These bonds share so unequally that the electrons are actually transferred rather than shared. And again, these occur between a metal and a nonmetal. Recall, however, that bonding lies on a continuum. Therefore, as we go from a zero electronegativity difference or a completely covalent bond to a large electronegativity difference, or a completely ionic bond, there's a whole lot of territory in between, where we have larger and larger differences in electronegativities. Therefore, we have increasing polarity, or increasing ionic character and decreasing covalent character. Electronegativity was first quantified by Linus Pauling, using the Pauling electronegativity scale. The general trend for electronegativity is that it increases across a period and increases up a group. Here you see fluorine has the highest electronegativity and francium the lowest. This is a relative scale with all values based on some standard. Usually in this class it'll be sufficient to use the trend to predict polarity rather than using actual values. And that's my dog Linus. He's named after Linus Pauling. So to summarize, nonpolar covalent bonds share electrons equally and are made of two atoms with approximately the same electronegativities, whereas polar covalent bonds share electrons unequally and are made of two atoms with different electronegativities. Here we see the electron cloud represented in blue. In a nonpolar covalent bond, the electron cloud is distributed evenly around the two nuclei of the atoms. In a polar covalent bond, it's unevenly distributed. Where there's more electrons, we have a partial negative charge. Where there's fewer, we have a partial positive charge. These symbols represent partial charge. Looking more closely at a polar covalent bond, take HF for example. This is both a bond and a molecule, since HF is a molecule that contains only one bond. Since fluorine has a higher electronegativity than hydrogen, it will attract the electrons towards itself, giving it a negative partial charge on the fluorine end and a positive partial charge on the hydrogen end. Notice that if we place these polar molecules in an electric field, they'll have a preferred orientation, with the negative end lining up with the positive end of the electric field and the positive end lining up with the negative end of the electric field. Here we see some partial charges for a variety of molecules that contain only one bond. Obviously, diatomic elements must have two atoms of the same electronegativity. Therefore, we'll have no partial charge and an even distribution of charge throughout the molecule. Notice, however, that as the difference between the electronegativities in the two atoms gets larger, our difference in charge gets larger, with LIF being a much more polar bond than HF, because the electronegativity difference is much greater. Considering now molecules with multiple bonds, such as water, molecules with polar bonds will usually exhibit a dipole moment. This means that these polar molecules will have a preferred orientation when placed in an electric field, as we saw with the HF molecule. This is due to the fact that there's a concentration of positive and negative charge in particular areas of the molecule. Take water, for example. Here we have two polar covalent bonds between H and O and H and O. Since the oxygen has a larger electronegativity than each of the hydrogens, it will pull the electrons in each bond towards itself. Notice that we're considering each bond separately to determine the overall dipole moment. This is a polar bond with electrons pulled towards the oxygen, and this is a polar bond with electrons pulled towards the oxygen. This means that overall, this molecule is negative on the oxygen end and positive on the hydrogen end. These are the partial charges of this molecule. That brings us to the end of this video. Let's review our goals. First, we looked at how covalent bonds differ from ionic bonds. Then we looked at how electronegativity difference determines bond polarity. And finally, we learned to identify partial charges on covalent bonds.